So, amino acids, proteins and DNA, 2017, paper 2. Let's have a look. Question 6. Draw the structure of the zwitterion formed by phenylalanine. So you need to find phenylalanine. You're not required to remember bases and amino acids. The structure of them are all in your data book. You draw out phenylalanine and you replace just one of the NH2s with an NH3+, and one of the COOHs with a COO-. You just do one of each. So if there's more than one, there isn't in this case, but if there's more than one, you just do one. Because what actually happens is the COOH that releases an H+, that then goes round and forms the NH3+ on the other part of the molecule when you get to a certain pH. It's something called the isoelectric point, by the way. If you have a certain pH, that's what happens. So COH becomes COO- and an NH2 becomes an NH3+ in just one place on each of one of those groups for each. So if there's a second NH2, you leave that alone. If there's a second COOH, you leave that alone as well. Draw the structure of serine at high pH. So high pH means that it's a base. You've added a base. You've got something like sodium hydroxide or potassium hydroxide at a high pH. That removes an H+ from the COOH. So high pH, a base like OH- will remove an H+ from the COOH and leave the COO-. You leave the NH2 alone. Similarly, if I had a low pH acid, the acid makes H+, and that would join onto the NH2 to make NH3+, and you would leave the COOH part alone. So at high pH, you're replacing COHs with COO-. At low pHs, you're replacing NH2s with the NH3+. And this time, unlike a zwitterion, you do it for all of the COHs. All of the COHs become COO-, or if you had it at low pH, all of the NH2s become NH3+. Again, in this case, there's only one of each, so that's easy enough. Draw dipeptides, phenylalanine and serine. Well, COOH and an NH2 react together and make a peptide link. It releases water in a condensation reaction, so you end up with CONH. And because phenylalanine and serine have got, as amino acids have, they could react the other way around, and it could be the COOH on the serine and the NH2 of the phenylalanine that react together to form a peptide bond. So that's why it can go either way. So you can swap the two amino acids over when you're forming a dipeptide. Okay, we've gone over this a little bit before, so how do we measure that? So you take the distance from the start line up to the middle of the spot, and you divide by the distance from the start line up to the top of the solvent front, and in this case it equals 0.62, which is D. So you're just measuring that with a ruler. State in general terms what determines the distance travels. The distance depends on how well the sample dissolves in the solvent being the moving phase, and how well it adheres, sometimes called retention, to the paper or the thin layer chromatography plate. Same principle, either way, the stationary phase. A practical requirement. So there's a few practical requirements you need. The solvent must be below the starting line, otherwise the amino acids will just dissolve straight into the solvent rather than rising up the plate. You should use gloves. That's another one, because if you've got amino acids on your hands, so if you touch the plate or the paper, you're going to put your own amino acids onto the plate. You should use a pencil line rather than a pen to draw the start line, otherwise you're going to get coloured inks rising up the paper. And if you're going to measure the distance to the solvent front, you can't let the solvent front rise off the top of the paper. You spray it, by the way, with something called ninhydrin so that you can see the amino acid spots, they show up, or you can use UV light to make them show up as well. A second TLC experiment, thin layer chromatography experiment, was carried out using 1,2-dinitrobenzene and 1,4-dinitrobenzene. So you've got those two structures there. Relative polarities. So deduce the relative polarities. In other words, which one's got the most polarity, which one has got the biggest delta pluses and delta minuses. Well, you don't need to have a look at the science really of that. You just got to be able to identify it. So it says under the same conditions, same solvent, the RF value of 1,4-dinitrobenzene was greater. So if it's got a greater RF value, it's risen further up the plate because the distance from the start line to the spot is bigger. So if it's risen further up the plate as, which one was it? In the experiment, the RF value of 1,4-dinitrobenzene was bigger. So 1,4-dinitrobenzene has risen further up the plate. Now, usually that means is that if something is polar, got delta plus and delta minuses, it sticks or adheres to the plate. So the fact that that one has gone further up the plate means it's not sticking or not adhering to the plate, and therefore it's not as polar. Things that are polar adhere to the plate and don't have big RF values, don't go up the plate that well. So 1,4-dinitrobenzene must be less polar. A third experiment was carried out using 1,2-dinitrobenzene. An identical plate was used in the same conditions, but the solvent was changed to be a mixture of hexane and ethyl ethanoate. The student stated the RF value of 1,2-dinitrobenzene in his third experiment will be greater. Is the student correct or not? So usually if you have a solvent that's polar, you change the solvent, and the solvent itself is polar, and ethyl ethanoate is polar, and ethanoate is an ester, it's got C, a double bond O section in the molecule. So it's got delta plus and delta minuses between the C's and the O's. The O's are electronegative. Ethyl ethanoate is polar, it's got delta plus and delta minuses. So if the solvent is polar, polar molecules dissolve better in polar solvents. So that polar molecule, whatever it is, 1,2-dinitrobenzene, will dissolve better in the ethyl ethanoate because that's also got delta plus and delta minuses. You get dipole-dipole bonding within the solvent and the molecules. You'll get intermolecular dipole-dipole bonding, so they're going to dissolve better. If it dissolves better than before, it's going to go further up the plate. If it dissolves better in the moving phase in the solvent, so the RF value will be greater, and the student is correct. Extract from the data booklet we've seen before. We've done this before in earlier videos, so I'm going to skip over that. Name the two types of group connected. Y is going to be a phosphate, so phosphates go up and down from the left-hand sections of the 2-deoxyribose, and onto the X part is where the bottom of the base joins in, where the blue line is at the bottom of the base. So where X is on the 2-deoxyribose, there's an OH if you look in your data book, and it's going to bond to the NH where the blue line is on the bottom of the base and release water, and then you're going to get a carbon of the 2-deoxyribose bonding straight to an N of the base as it releases H2O, an H from the bottom of the NH on the base, and the OH where that X now is on the 2-deoxyribose. What have we got here? Complete a diagram to show I've got adenine. Adenine is linked to a hydrogen bonds to a molecule. So we can see adenine is going to bond to thymine. It's going to have 2 hydrogen bonds from the NH2 on the top of the adenine round to the O on the thymine, with the lone pairs of electrons on the thymine of the O bonding to the delta plus of the NH2, and then going round again, the lone pair of electrons on the N of adenine, hydrogen bonding to the H pluses on the NH. each of the thymine, 2 hydrogen bonds. So you've got to draw your thymine in, flip it, you've always got to flip it, mirror image it, so that the 2 hydrogen bonds join on and not overlapping. Now, one thing that I would lose a mark there for, and I couldn't do it on my computer, is that there should be dotted lines between the 2 bases rather than solid lines. You show a hydrogen bond with a dotted line.